Good morning to all of you.
Morning, sir.
Morning, sir.
Okay, we will start today a new chapter. Actually, penetrating to design. In our all previous discussions.
Morning, sir.
In all previous discussions, whatever we had made.
So we can hear you properly.
Oh, you cannot hear?
Hello?
Now? Now? Hello? Are you hearing me?
Yes, sir.
Okay. So now all the discussion whatever we had in our previous days, it was with respect to the materials for RCC and different.
Hello, sir.
Not yet audible? Are you looking this class in your laptop or mobile?
The voice is not clear, sir. Yes, sir.
Okay. Now you will get these things also by I'll send it also as like the previous ones. Okay, you just take your attendance. You need not copy at this moment. You will get all these things. Okay, so all previous discussions whatever made, it was with respect to the ingredient materials, and then it was composed to concrete, then it was composed to RCC. Okay, and we had got the advantage disadvantage of RCC and how we can get all these things. So we now got the RCC. Now we want to this RCC utilize in our structure, whatever we are going to construct. Okay, and when we talk about structure, now structure, it may be single, it may be of single material, and it may be used in multiple material. A building, we can say as a structure. A dam, we can say as a structure. A boundary wall, we can say as a structure. A retaining wall, we can say as a structure. You get all these structures. Now, all these structures are composed of some element. Now, when we are composing some element, some numbers of element, but we are taking this some numbers of similar shape. Now that similar shape is this the easiest one is beam. You can visualize a beam, you can see a beam if you are in your house. In your house, if you see vertically upward, you will see a beam. Now for beam, there are three dimensions. One is lengthwise, another is depthwise, right? Now with respect to our momentum, with respect to our strength of materials, since we are having three axes, the axis parallel to the breadth, is normally designated as the ZZ axis. The axis parallel to depth is normally considered as YY axis, and axis the lengthwise direction is normally called XX axis. Okay. Now, if all structures are composed of some beam element. Okay, beam itself is a structure. Now, if we want to construct and design a slab, length, it is having breadth, it is having thickness. The length and breadth is comparatively larger than the thickness. Okay, but in case of beam, the breadth and width are almost same, and length is comparatively larger than the breadth and depth. That's why beam is normally considered as uniaxial member, and slab is considered as biaxial member, two axes, or one lengthwise axis, one breadthwise axis. Third dimension is very small. So we are going to construct this beam element composing converted to say slab or wall or retaining wall with the help of this RCC. So since this is a beam element, since it is a beam element, length is comparatively larger than the width and thickness. Okay, so since it is a beam element, there will be support at the two end. Hmm? Support at the two end. Now, if the support is just simple, then it is called simply supported beam. And if the beam is having support free, then it is called cantilever beam. If the beam is rigidly connected to the supporting member, the supporting the columns rigidly connected, then it is fixed beam or a frame. So the load will act. Normally, load acts parallel parallel to y-axis. In normal case, our vertical, and z-axis is transferred to z-axis is transferred to z-axis. Okay, so in normal case, loads are acting parallel to y-axis. So if load is acting parallel to y-axis, think about when you had studied in strength of materials or structural mechanics one, bending moment and shear force. The load is acting vertically, and because of this load, on the beam, two important force arises. One is bending moment, and another is shear force. Okay, because of the bending moment, the beam has a tendency to deflect, bend, and because of the shear force, the beam has a tendency to shear off perpendicular to the longitudinal axis. Right now, here we are talking limit state of collapse. That means out of the three methods, whatever we have got in our one of our last class, the last one was a limit state method. That means we will study the limit state method of collapse, limit state method of serviceability. Okay. Now, since the beam is see first sentence, if you see the design of limit state collapse in flexor shall be based on the there should be one word, the following assumptions. Now, out of these assumptions, study the chapter bending stress distribution. Okay. Now, a beam is consist of some slice having dimensions breadth and depth. Having dimensions depth and breadth. Some slice, when you some slice along the longitudinal axis, it converts to a beam. So if the slice, there is a plan, vertical plan. There is a vertical plan. Now you imagine if you are having some element, and if you see a vertical plan, it's a vertical plan, the surface, if you cut by a smooth instrument, you will get the plan, vertical plan. Now, the first condition is plan section normal to the longitudinal axis remains plan after bending. Whether it is really true or not, that is a question, but it is observed. This is an assumption adopted by any and every engineer. The plan section before bending, before the application of the load, the beam is not getting any bending. There will not be any deflection, but due to application of the load on the member, the beam has a tendency of getting deflected. And because of the deflection, what is happening? I told you in our previous discussion also, some part of the section subjects to contraction and some part subjects to tension. So if you see from extreme outer surface, there will be maximum tension or contraction depending on the surface, and gradually towards the mid depth, the contraction or elongation decreases. At some point, there will be zero. That means that is the transition point. Immediately after crossing that point, the property, of the element at that particular location, at that particular location, it changes. It changes from tension to compression, or from compression to tension. Tell me, am I audible?
Yes, sir.
So the plan section normal to longitudinal axis remains plan after bending. See, in bracket I am writing that is in an initial straight beam. The strain varies linearly over the depth of the section. Strain varies linearly. Strain means strain we know, rate of change of deformation. Rate of change of deformation. If the strain is longitudinal, then longitudinal deformation divided by original length. The original length remains same. Original length remains same. So if deformation changes, strain changes. So the deformation at the central point, deformation is zero because it is a transition point from tension to compression, or from compression to tension. As from midpoint you go to the extreme surface, upper surface or lower surface, the change of deformation increases. So strain at the extreme outer surface is always more. And if you plot, you will get a straight line. That means the section in the vertical, it remains same. Maximum strain in concrete at outermost compression fiber is taken as 0.0035. Again, this is assumption. Now here, before going or entering inside, I will have to talk one thing. Okay. Now see, at the beginning also we have told that we considered the strength of concrete. Whatever strength, whatever resistive force that we are getting at the end of 28 days, it is called strength of the concrete. So if it is M20, that means at the end of 28 days curing, if the concrete block is broken, then stress induced or force exerted per square millimeter should not be less than 20 Newton per millimeter square. Now at that time, what is the strain? Now if you plot, or if you go to any concrete technology book, or you have told something, if you plot stress strain curve for concrete, you will not get any defined shape. We will not get any defined shape, whether it is straight, parabolic, hyperbolic, we will not get it. So that's why, or that it is assumed, stress strain. Now it is observed that maximum strain is considered 0.0035, that means 0.35%. Now why it is taken at the end of 28 days, whatever strain we are getting, beyond that also there will be change of deformation, but change of deformation will be negligible. So that's why it is considered that the maximum strain will be 0.0035. Okay, so the stress strain curve for concrete is not giving any particular shape. Okay, but when we are to utilize in our real field, we should get some particular shape. Only in that case we'll be able to utilize in our real time, in our real we'll assume something. Okay. Now, stress strain curve of concrete in flexural compression is as given in figure 21 IS 456 2000. Okay. Now see here, there is a curve, stress by strain. The topmost curve, that is the, again, that is the assumed curve. That is the assumed curve. This curve is accepted by, IS, Bureau of Standard, BS, Bureau of Standard. This curve is accepted. Now, what is happening here? You see, what is here? You see, from strain 0 to strain 0.002, it is a curvilinear. But from strain 0.002 to 0.0035, it is considered with respect to constant stress. With respect to constant stress. That means strain is increasing, but stress remains constant. It's an assumption. It is assumption, because whatever change of stress will be observed, it will be very, very negligible, which is approximately equal to FCK. Now, what is this FCK? What is this FCK? It is characteristic compressive strength of concrete. Characteristic, that means stress attained by the concrete after casting and curing 28 days. Whatever stress we are getting, that is the FCK characteristic strength. No, it is not the exact definition. The exact definition of FCK we will discuss slightly later. Right? Now, this curve, here you see, for practical region, the topmost curve is the actual result. But because of some variations, on which we have no control, the engineer, mason, owner, etc. are not having control. So that's why whatever characteristic strength we are getting at the end of 28 days, that particular strength is reduced. The 67% of the strength, whatever we are getting at the end of 28 days, is taken. So that particular curve is taken. So that is the design curve. That is the design curve, the curve with respect to 0.0. But remember, strain remains constant. Stress is reduced. Now, why? There are some problems on which we are not having control. We cannot control it. So we should utilize some conception. So the all over the world, it is assumed that, okay, whatever characteristic is there, we will consider the 67% of that. Okay. Now, next curve you are getting, see, 0.67 FCK by gamma m. Now, what we had done when we had discussed in our last class, by a factor that is called partial safety factor. This gamma m is partial safety factor. Okay, so finally we are going to utilize the bottom curve in our real design calculations. Okay, do you follow? Any doubt? Anybody? Any doubt? Anybody? That means stress strain curve, this is considered 0.67 FCK by gamma m. Now, verbally in last discussion, I had given the value of gamma m. The gamma m partial safety factor 1.5. Partial safety factor for concrete is 1.5 and partial safety factor for steel is 1.15. Those values, whatever curve I had drawn here, this curve is available in IS 456 also, and whatever assumption we are now discussing, this is simply reproduced from IS 456 only, where we kept here for discussions. Okay, then the tensile strength of concrete is ignored. Now, if there is strain difference, if there is stress difference because of the deflection, normally the bottom part subjected to elongation and upper part subjected to contraction. The transition point is called neutral point, and the axis parallel to the axis parallel to the longitudinal neutral axis. Longitudinal neutral axis. And if you see, if you try to imagine a beam having length L, width B, depth capital D, and if we cut along the lengthwise, we will get the lengthwise section, longitudinal section. And if we cut along the y-axis, it is cross-sectional. It is cross-sectional section. And if you see longitudinal section, you will get there is deflection at the midspan. It is sagging, and near the support it remains constant. Because of that, with respect to neutral point, the bottom part will be subjected to extension, upper part will be subjected to contraction. Now here, if the bottom part is subjected to contraction, tension, then bottom part will be subjected to tensile stress, tensile stress. Okay. Since we had already discussed that strain or tensile capability of concrete is very much negligible, only 1/10 of the compression. So that part is neglected. It is really giving some resistance, but that whatever resistance is there, that part is neglected. That means the tension, whatever is going to induce, will be resisted by the steel. Okay, the maximum strain in tensile steel, epsilon st, at ultimate limit state shall not be less than epsilon su. Strain at ultimate position, defined as, now this expression, epsilon su is equal to 0.07 fy by es plus 0.002. Okay, now see, stress by strain. Stress by strain is constant. Now if I transfer epsilon su towards right and es transfer to left and eliminate 0.002, so this expression, whatever you had got in your class 8, okay, from that it is taken. And when 0.002 comes, that we'll see later. Okay, so ultimate strain is equal to 0.77. Now where from this 0.87 comes? Where from this 0.87 comes? Our expression was stress by strain is equal to Young's modulus, E is equal to F by epsilon, strain. Now F, the value F we got, Fy means yield stress. Now where from this 0.87 comes? Okay, where from this 0.87 comes, that figure I had not drawn here. It is just like with respect to concrete. With respect to concrete, in concrete we had got, with respect to this curve, we had got the stress is 0.67 fck by gamma m. Now 0.67 is because of uncontrolled variable factor. There are some factors on which we are not having control. That's why we are taking a factor 0.67. Now with respect to steel, the steels are manufactured in the factory, so there is no possibility of uncontrolled variable. So 0.67 can be replaced by 1. 0.1. Then FCK. Now in case of concrete, the characteristic strength is represented by FCK, and in case of steel, it is represented by Fy. Okay, so in case of steel, this thing will be can be represented by point Fy by gamma m. Now gamma m with respect to steel is 1.15. Okay, so 1 divided by 1.15 is approximately equal to 0.87. So that's why it is 0.87 Fy. Very simple. Okay. The stress in reinforcement are derived from the representative stress strain curve. Steel is shown in figure 23 IS40. This I am not bringing here. This you will be able to see in code or in any textbook. Okay, and these the conception of this is also you are having because you had studied with respect to this from your class 8 standard. Okay, so with the help of these assumptions we will be able to enter our real field. Will be entered to our real field. Now let us come to the real field with the help of assumptions. Now here is a pen. So this is the actual chapter. Analysis of single reinforced rectangular section. Now what is single reinforced rectangular section? What is single reinforced rectangular section? See, we had in our discussion before that in a beam, when load is acting, because of that, the beam has a tendency of deflection. And because of the deflection, the bottom part has a tendency of expansion and upper part has a tendency of contraction. Since concrete is strong with respect to concrete, so with respect to compression, so the upper part, there is no danger of failure. There is no danger of failure. So in upper part, we do not require any other help to resist the compressive stress that is going to induce because of the external load. That means in upper part, we do not require any reinforcement. That means we do not require to utilize steel. But bottom part, it is having tendency of expansion. The concrete is weak in tension, and also we have made an assumption. Tension in concrete is neglected. So if that is the situation, then who will resist the tension? Concrete in tension zone is neglected. So we require some other material which is called reinforcement. Normal of reinforcement is steel. So we are providing, that means reinforcement only on one piece. We are providing reinforcement only on one piece, that is on tension piece or tension zone. One zone, one piece, we are providing only on tension zone. And since the reinforcement is utilized only in tension zone, that's why that particular beam or that section will be called single reinforced member, single reinforced section. Now, why it is the effect? Now let us now see the figure. See the figure. Are you looking at this figure? Anyone give the reply? This note is visible to you in your laptop or mobile?
Yes, sir.
Yes, sir.
Now see here, this figure, what has happened, I had drawn in plain paper, then I had scanned it, and then I pasted it. Okay, now see the extreme left, it is a rectangle. Rectangle means the cross section of the beam. If you cut the beam vertically, and if you from the length direction, you will see that part. And at the bottom, a part is there. A part is there. It is hatched. It is hatched. For simplicity, it is hatched. Actually, those are the reinforcement. So only reinforcements are provided here. No, these are the reinforcements. Okay, no reinforcement are available in this. In this. Okay, now come to this figure, next figure. This is the strain diagram. And last one is the stress diagram. With respect to, are you looking my hand? No. No. Are you looking my hand? No. Okay.
No, sir.
You are looking my hand?
Cannot see, sir.
So the camera is bit.
You cannot see, because it is obstructed by the paper. Okay, this second figure is with respect to strain. So along the depth, now here, the strain is compressive, maximum strain. As you come along the depth, the compressive strain is going reducing, and somewhere the strain will be 0. And if you go beyond that, there will be strain, but strain will be tension. So here, here. This is the extreme upper surface. This is the extreme upper surface. So here, since here strain is maximum, so here stress will be maximum. Strain is reducing, so stress also reducing. Correct? Strain is here 0. Stress is here 0. Here in this figure, I have drawn the strain on also, but here I have not drawn in stress diagram anything because of our assumption. Tension is resisted. Tension is resisted by steel. Tension by steel or concrete in tension zone. Concrete in tension zone is neglected. That's why the stress diagram stops here. Okay. Now here see the peculiarity. So this is 0. This is 0. It is visible? Huh? Is it visible for all of you?
Yes, sir.
No. So here it is 0. Correct. Now to come. So that particular point is this one with respect to this figure. So as this is stress and this is strain, so this is stress. That figure is with respect to stress and depth. See, the stress is going on increasing in a parabolic format, and it is maximum here. After that, stress remains constant. Right? Now see here. So this is the neutral point, and gradually stress increases on upward phase. So stress. So here it is maximum. Then stress is constant, and constant value comes here. Okay. Now these are in our assumptions. Now see here. Assumption B, at outermost fiber, stress is taken 0.0035, 0.0035, and at maximum stress, strain is 0.002. That means up to strain point 002, strain increases, stress increases. But beyond point 002, strain increases, stress remains constant. Okay, so that means from this point to this point is the depth of the member. Is the depth of the member. Now see here, strain at extreme compression surface is 0.0035. So this according to assumption, and at the depth, some value depth, the strain is 0.002. This is with respect to our assumption. That means up to the strain 0.002, stress varies in a parabolic format. So this is the point. Up to this point, stress varies parabolic format, and beyond that, strain varies, but stress remains constant. So this you have to follow. Okay, now the question is coming. This point, up to what height or up to what depth? Up to what depth stress remains constant? Or at what depth strain is 0.002? So okay, so using this figure, now see here, when this XU is the neutral axis depth, XU, this is the neutral axis, this is the neutral axis depth, XU, right? Then Y2 height from 0 strain to 0.002 strain, from 0 strain to 0.002. So this is the Y2. Okay, so Y2 is equal to, so from similar triangle, right? How we can find? So this divided by this is equal to this divided by this. Some two similar triangle, right? So this value is known to us 0.002. This value is known to our 0.0035, and this value is known in terms of unknown, XU. Okay, so from this similar, this is equal to this divided by this multiplied by this. So we got height Y2 is this ones. Then H1 is height from 0.002 to 0.0035. That means this part. Okay, so this part is equal to this part minus this part, XU minus Y2. See, XU minus Y2. Y2 is 4 by 7 into XU, so ultimately 3 by 7. Okay, we got it. Now we can enter. Now see here, well, from this 0.447 FCK we got. So this 0.447 FCK we got from here, from this expression. 0.67 FCK divided by gamma m. Gamma m is 1.5. So 0.67 divided by 1.5 is approximately equal to 0.447 FCK. Okay, so for this extreme compression at extreme compression level is 0.447 FCK. So this is known to us. Now see here. Now come to the stress diagram. Now in stress diagram, it is observed that this part, the stress diagram is rectangular, and this part is parabolic in nature. So we want this area and this area to find out the maximum compression. Now see here only these deductions. Okay, when C1 compression on rectangular part, on rectangular part. So rectangular part is 0.447 into rectangular part. This rectangular part is y1. Rectangular part is y1. This part is this is y1. This is rectangular part. This is parabolic. Okay, so 0.447 width of the member into depth of the member. Width of the member and the depth of the member multiplied by intensity of stress. Intensity of stress is constant. Width is b. Depth is xu. Depth is x bar. Not xu. X bar. X bar means no. Depth is y1. Depth is y1. So you see here. Okay. 0.4. This b into y1. B into y1 is the area of section of the member for compression zone multiplied by intensity of stress. This is the intensity of stress, 0.47 FCK. So it is ultimately come 0.19 FCK. And similarly, compression for the part parabolic, B into depth. B into depth. So this depth is, it is parabolic. It is not acting throughout the area. So it is, that's why y2 or for that 2/3 of y2. This is a general expression. This expression you had got in your school level. So I don't think it is difficult thing. So we got this is the 0.171 FCKB into x. Okay, so total compression is equal to compression in rectangular part, compression is in parabolic part. So C1 plus C2. So ultimately we got 0.36 FCK B into XU. The C is equal to 0.37 FCK B into XU. Now this expression, this particular expression, you will get in your IS 456 F appendix. So if somehow, if you forgot, not to worry, this is available there. Okay. Now, since there is a compressive force acting on an area, so definitely there will be this force, the C is the force. It is not the intensity, the force. So it has some point where it has some point where it is acting. It is some point where it is acting. Okay, so that is the point of contraction, or that's why it is line of action of compression C with respect to extreme compression fiber. See here, see this figure, see this is C, this is C. So this depth from extreme compression surface is x bar. So how we'll be able to find out? So again, finding this, you had studied even in your school standard, multiplication of moment x bar. 0.36 FCK B into XU. This is the C into x bar. That means we are taking moment of all the forces with respect to extreme upper surface of the section. So 0.139 0.139 FCKB into multiplied by half of y1, multiplied by half of 1, so half of y1. C2 0.171 FCKB into XU. So again we require the distance of this C2 with respect to this. So we got XU minus 5 by 8 into Y2. Again, mathematical per subject in your other semester or even in your school. Okay, so ultimately what we got, XU is equal to approximately 0.42 XU, right? Okay, this expression, this means a line of action of total completion on the cross section is equal to 0.42 XU. That means 0.42 times neutral axis depth. See, up till now we do not know the neutral axis depth. We do not know the neutral axis depth. So it is unknown. Axis with respect to an unknown. So now this XU is equal to 0.42 XU. This is also available in your uh, IAS 456. Okay, so now our interest to find out XU, value of XU. Okay, now we see our cross section is having one neutral point. The area above the neutral is subjected to compression. The area below the neutral axis is subjected to tension. Right? Now, one assumption I have not written here. One assumption I have written. That assumption is if there is no longitudinal force acting on the member, then resultant axial resultant effective axial force. So resultant means there is compression and there is tension. So total compression plus total tension should be equal to 0. So total compression is equal to total tension. So this I am writing, total compression is equal to total tension. Right? So total compression we have got 0.36 FCKB into XU. Now total tension I had written at the top. Total tension is area of steel multiplied by stress induced. Stress induced is 0.87 Fy. That I had already how 0.87 Fy is obtained, that I had already got. So total tension. So total compression should be equal to total tension. So this we got. So from this expression we got XU is equal to 0.87 Fy AST divided by 0.6 FCK. Now here on left hand side, all the informations will be known to you, so we'll be able to XU. Or if XUs, then we can find out other values. So this is one important expression. Now this expression, it is not difficult. It is very simple. It is very simple. It is very simple. Okay. Okay. So something I got. Then there is a ratio. It is just ratio. XU by D is equal to, now see here I am reading here, which is the expression annexure G. So this expression is also available in your IAS 46 in annexure. Okay. So if at all you forgot at the time of calculation of the numerical problem, you just open the code, you get it. Okay. So this is very simple. Now it is question, since our sector is a limit state of collapse. So up till now, whatever we discuss, nowhere we mentioned the condition of collapse. But according to theory, limit state of collapse, we are to go up to the point of collapse. We have to find out the strength with up to the point of collapse, or we have to find out the section required to resist the external load up at the point of collapse, or we have to find out the amount of stress still required at the point of collapse. So that collapse we have to utilize. That collapse we have to utilize. Okay. Now see here. That's why it is called a limiting neutral axis depth. Okay. Now this XU, this XU is actual neutral axis depth. Now onwards, we will stop. No, before this we had called the neutral axis depth. Now onwards we will call XU is equal to actual neutral axis depth. Okay. So when there is actual, there may be some other values also. This neutral axis may be smaller, maybe smaller than this XU, maybe small higher than XU, maybe neutral. If XU is at neutral, then it will be called limiting neutral axis. So the limiting neutral axis is normally represented by XU max. Okay, so limiting neutral axis depth is XU maximum. Okay, now this epsilon ST maximum strain tensile is this expression I had already given. Now come to the considering the strain diagram. Again, we will go, strain diagram is this one, but we should draw a defined figure. We should draw a defined figure with respect to that one, but similarly, it will be similar. Okay. Now see here, what I have written here. XU maximum by D minus XU maximum. So this is your XU maximum. Say this is your XU maximum, right? And from extreme compression surface to center of this steel is D. Okay. So XU, what is written? What I have written here? XU maximum by D maximum. That means this depth XU maximum divided by D minus XU maximum. That means from here to here. Okay. So if it is this and denominator is this, then we have to consider this and this. So that's why it is written what? 0.0035. 0.0035 divided by this. Okay. So just permutation combination you had got. If you XU minus D, if you deduct the numerator from the denominator, so denominator this will go, so only the 0.0035, where it is 0.0035, so 0.0055, right? Now see here, Fy is known to us, epsilon S is known to us. So we are getting, this is a ratio. XU maximum by D is a ratio. As the D varies, XU varies. So we are getting a relation of this. So grade of steel, XU maximum by D, Fe 250.53, Fe 415 48, 0.48, Fe 500 0.46. So these informations will be required. XU maximum. Okay.